All right, so this is chapter 8. We're going to talk about atoms. So a little bit of this is going to be review. Some of it's going to be some new information because we're going to start off with talking about things like the discovery of the different parts of an atom. And then we're going to take a tour of the periodic table. So I have posted a periodic table up on Panther Learn. If you don't have a copy of it yet, you might want to go ahead, pause the video, and go and print yourself off a copy or just download it to your desktop. It should look like this. So this is the periodic table that you'll see me use, and this is the one that you can use for your exams. So I would highly recommend that you either print it off or have a copy of it on your desktop, because you will probably not be able to pull it up when you open your exam, since the browser will be locked on your exam. And this is a nice version of it because it's got all of the different information that we're going to be using in the course. So let's get back into the slides. So first thing we want to look at is the different pieces and parts, and we're going to actually go through and talk about the discovery of the different parts of an atom as they were discovered. So the first part of the atom that was discovered was actually the electron. So it was discovered during studies of electricity. So when scientists were working to observe currents, what they would do is they would actually build these cathode tubes. So they would put these metal plates on either end. They would vacuum out the air. So there was nothing inside, at least as far as they could tell, there was nothing inside. And then they would hook up a voltage source to this cathode tube. And when they turned it on, when they turned the voltage on, they would get cathode rays, is what they called them. It was this greenish beam that would run from one metal plate to the other. So they started to wonder what this greenish beam was. So if we could go back and look, because the thing is that they were pretty sure this wasn't actually just like the electricity. They thought maybe it was actually like a material of some sort. So what they did is they set up a new experiment. So J.J. Thompson in 1897 discovered electrons using these cathode rays. So he actually figured out that these were a particle, and a particle that had a charge. So what he did is he took this cathode ray and inside of it put plates that carried a charge. And then what he found is when he created a positive charge, then the beam was going to be bent or deflected away from a negative charge. So whenever he exposed this end to a negative charge, the beam would bend away from that negative charge. And so this told him that these particles, or this cathode ray, was actually negative, because what do like charges do? Like charges repel. And so you've discovered that these particles were negatively charged that were being created from that voltage. And so you also ended up measuring the electrons' charge to mass ratio, and he even kind of figured out how big they were. So Robert Millikan in 1906 went even farther and determined what the charge of an electron would be. So if you remember coulombs, we talked about those when we talked about electricity. He determined that the actual charge of an individual electron is this really tiny number, because if you remember your exponents, -19 means that it's going to be a really small number. So the decimal point is going to move this direction 19 places. So put together with Thomson's ratio for the mass of an electron, it was determined that an electron was 9.11 times 10 to the negative 31st, or 1,840th the mass of a hydrogen atom. So electrons were found to be very, very tiny, which is something that we realize now today. So the next thing that we started to think about was, well, if there are negative electrons in these atoms, there must be something else that's there, that's holding them. Since negative charges fly away from each other, there has to be something positive that's keeping them in their place. So Thompson and Millikan determined charge and mass of electrons, but we know that these atoms are electrically neutral. So what's canceling out the electrons? Well, Thompson proposed this Plum pudding model. Basically, that the electrons are stuck in a positive, massless blob. Plum pudding being, the dish of the day. So basically, there's this big lump that is positively charged, and then the negative electrons are just kind of stuck in it like raisins. And so this model lasted for a little while, but not for very long. Because along came Rutherford in 1907. He was actually studying radiation. So he was looking at radioactive sources and trying to figure out information on those. So what he was doing was aiming this radiation at this gold foil. So you can see this foil right here in the center. So he would aim his radiation source right at it to fire the radiation at the gold foil. And then around the outside was this detection screen. And the way the detection screen worked is when the radioactive particles hit the detection screen, they would light up. And the thing is as he made his observations, he found most particles went through. They would go through the gold plating, but some of them were deflected at pretty large angles. So you can see this one over here is going over in this direction, which is not something he expected. He expected them to pretty much go straight through, maybe some deviations, but you pretty much expected all of them to go through this plate and end up here on the back side. But he found them hitting way over here and way over here and over here, which told him that there was something that these particles were hitting in the gold. And it could only happen if there were two positive charges repelling each other. That would explain this huge deflection. Just like the negative charges of electrons are going to be repelled, same thing here. Two positive charges, the positive charge from the radioactive element and the positive charge from the gold atom. And so when they came in contact with each other, or pretty close contact with each other, they repelled each other and would shoot off in a new direction. So that meant that atoms must have a tiny, massive positively charged nucleus, not this big gooey section that the electrons were hanging out in. So knew then that there's this nucleus, so this really tightly bound area that was positively charged, and we knew that there were electrons. So Rutherford estimated from his research with that gold foil experiment that the electrons must be moving around the nucleus at a distance about 100,000 times the radius of the nucleus. And this is just because of the deflections and the amount of times that he observed those radioactive materials going through the gold foil. In fact, if we go back, you can see here, this is the model that he constructed. So he estimated there had to be a huge amount of space in between these nuclei in order for those particles from the radioactive source to be passing through most of the time. And so that's how he ended up being able to build his calculation about this 100,000 times the radius of the nucleus for the electrons. So that means that the atom is mainly empty space. So you can see this is our classic model of the atom. I'm sure some of you have seen this before. So we've got a very tight packed nucleus and then this big empty space that the electrons are moving around in. So the proton then was identified as the positive particle in the nucleus from Rutherford's work. The neutron was the last thing to be identified. And if you think about it, that makes sense because the neutrons are neutral. So it's very hard to test. You can't really throw something neutral at it because they don't have charge either, and so that wouldn't react. It actually took until 1932 for a gentleman named James Chadwick to actually discover that neutrons were there as well. So as I said, atoms are small. In fact, so tiny that each time that you breathe out, you are breathing out 10 billion trillion of them, which also means each time you breathe in, you're breathing in 10 billion trillion of them. So, I mean, think about that. That number is a really hard number for us to kind of wrap our head around. So you're breathing in tons of these guys every time you breathe in and out. They're so tiny that we can't see them with visible light. The wavelengths, right, these guys, of light are too big to hit atoms individually. They can hit them when they're in a huge group, but to hit them individually, they're too small. The wavelengths just pass right in between them. So in order to be able to see atoms, like in the picture that you see up here, we have to use what we call a scanning probe microscope. So the way scanning probe microscopes work, I figured out how to do this today. So if you're familiar with a record player, so you've got a section out here that would have the little needle on it. This is the part that you would set on the record. And then it's got an arm that comes back. And so when we play a record, this section is going to set in the groove and it bounces up and down to make music. Well, this section of a scanning probe microscope is going to bounce up and down as it runs across these atoms so that we can see it. Now, obviously, this is much smaller than a record player arm, but that's the general idea of how a scanning probe microscope works. All right, so the other thing, like we just saw with Rutherford's calculations, they are empty. To give you an idea of how empty, an atom the size of a medium-sized airport. Now, medium-sized airport, that's Columbus Metro Airport, right? So that's the John Glenn Airport in Columbus. That's a medium-sized airport. So imagine that size of an airport, and then you stuck a basketball in the center of it. The basketball would be the nucleus. So that's how big and empty they are. The rest of the basketball is the nucleus. The rest of that space is where the electrons would be hanging out. All right, so I'm going to stop here and we'll pick up with talking about the atom, atomic number, and things like that in our next